Okay, so and again, I know, well, I hope you guys did a little bit of this in physical science, but I'm going to go through the process again, okay? And now I'm going to give you an example of a compound that's bonded ionically. Okay? We're going to start off with, gosh, I don't know. Let's do potassium. Oh, I don't know. What do you guys want to do? Bromide, since we already talked about that. Now, how many valence electrons does potassium have? It has one valence electron. You guys may remember seeing something like this before. And how many valence electrons does bromide have? Or bromine? Bromine. What group's it in? Group 7A. Therefore, it has 7 valence electrons. Does this look familiar at all? Okay. Now, what does potassium have a tendency to do when it forms an ion? Well, it's a metal. Metals lose electrons. How many is potassium going to lose? One. Bromine, being a nonmetal, has a tendency to gain electrons. How many will bromine gain? One. Oh, isn't that handy? Okay. Now, this isn't exactly what goes on, but it gets the point across, okay? So now, potassium has lost an electron, bromine has gained an electron. What's the charge on potassium now that it lost an electron? 1 plus. Bromide is now 1 minus. And as you guys all learned back in 2nd grade when we were learning Roman numerals, opposite charges attract. Boom. That's how substances are bonded ionically. It's just a force of attraction between two oppositely charged particles. Okay? Whereas in a covalent compound, for reasons that we won't get into until, gosh, hopefully right before Christmas, fluorine gas has the formula F2. Now, what kind of compound is fluorine? Or sorry, what type of substance? Is it what types of elements? How is fluorine going to be bonded? 2 nonmetals, right? Both of them, no, not metals. So it's going to bond covalently, in which case the electrons are going to be shared. Very good. How many valence electrons does fluorine have? 7. Now, even though all fluorines are fluorine is fluorine is fluorine, I'm going to use different colors for the electrons so you can see that they came from different places. Not that electrons are different. Okay. So each fluorine atom has 7 valence electrons. You guys remember doing anything like this before? Yeah. Okay. And we've already talked about how, and you guys came in with some knowledge that in covalent bonding, valence electrons are shared. Okay. So what's going to happen is, since each fluorine needs 1 more valence electron to complete its octet, they're going to share these. Okay? And so we would write that something like this. Maybe you've done this before. Have you guys done something like that before with little lines that represent a pair of shared electrons? Okay, well, we're going to do that a lot. That'll be after Christmas, but we're going to do that a lot. Okay, so anyway, clearly a difference. Here in ionic compounds, we have electrons that have been transferred from one species to another. Covalent, they're actually sharing the electrons. We'll get more into bonding and what that means later. Okay. With that being said, I'm going to break this down into, we're going to focus mainly on ionic compounds first, then we'll roll into covalent compounds, as far as naming them is concerned. All right. The next little piece there says, writing binary ionic formulas. Okay, all those words mean something. Binary means 2. Ionic means, okay, we're going to have form between metals and nonmetals, okay? But since I said binary, that means there's going to be single ions, single atomed ions, monatomic ions, okay? And we're going to write their formulas. That means we're going to use the symbols. So all those words mean something. Gives you a little set of instructions. This is easy. You may have done this before. When you're given the formula, you're going to write the symbol, or when you're given the name, you're going to write the symbol and charge of the cation first. Remember what a cation is. Positively charged. Then you're going to write the symbol and charge of the anion, which is negatively charged. Here's the deal. The sum of the positive and negative charges has to equal 0, mathematically. Okay? Or in other words, the charge has to balance. A couple of different ways you can do that. So it has a net charge of 0. Let me come up with a substance here that's not already one of the examples. Let's go with, I already did potassium. Let's go with magnesium oxide. Okay. So first of all, is this an ionic compound? And if it is, how do you know? What's the evidence that this is going to be an ionic compound? Go ahead. Has a metal in it. Has a metal in it. Okay? If there's a metal, it's ionic. So what we're going to do, as it says, is write symbol in charge of the cation, which is Mg with a 2+ charge. Then we write symbol in charge of the anion, which is going to be O with a 2-. Okay. So now, we've written that in part A of number 3. If the charges cancel, do these charges cancel? Okay. So you just write the formula as it is. So you would write MgO. Notice how many charges I wrote in the final answer. None. Okay. You don't use charges in the answer. Okay. So everyone hunky-dory so far. Okay. Now let's go with another scenario. What if we have? Let's go with. Gosh, I don't know. Calcium. We'll go with fluoride. Okay. First of all, is this an ionic compound or not? How do you know? Which one is? Calcium's a metal, right? Calcium's a metal. So we're going to write the symbol in charge of the cation, which is Ca with a 2+. Symbol in charge of the anion, which is F with a 1-. Do the charges cancel? No. Okay, we got two different ways we can do this. One is probably the best way. Another way will work like 90% of the time. The first way I said is use the lowest common multiple of the charges. Well, what's the lowest common multiple of 2 and 1? 2. Lowest common multiple of 2 and 1. 2. Okay? Well, how many calcium ions am I going to need to get 2? Just 1. How many fluoride ions am I going to need to get 2- charges? 2. Okay? And so I would just write a 2. So CaF2. Whereas the subscript indicates the number of those ions. So far, so good? Now, the other way that it says is something about this crossover method. Do you guys see that? If you think this through a little bit, isn't that essentially what happened? Is that this 2 became a subscript over here, and the 1 is an understood subscript over here? Still get the same thing. This is going to work like 90% of the time, but there will be some times where it doesn't work. So I think that first thing that we did where we found the lowest common multiple, that's kind of a foolproof way to make this work. Okay. Any questions so far? And there's a couple more examples down there. I think I put what? Sodium chloride, which you guys have known sodium chloride to be NaCl for a long time. And then I've got aluminum oxide. Let me walk through the lowest common multiple part on aluminum oxide really quick. So if I had aluminum oxide, clearly the symbol in charge for aluminum is 3+, oxygen or oxide's 2-, right? What's the lowest multiple of 2 and 3? 6?
Oh, yeah.
Lowest common multiple of 2 and 3. 6. 6. Okay, so how many aluminums do I need to get the 6 positive charges? 2. How many oxygens do I need to get to 6, 3? And so I turn out the same way, whether I crossed it over or did the lowest common multiple thing. You guys good? All right. I believe on the next page I left a little blank there for you guys to do some more examples.
Yep.
Okay, so let me throw some more examples. I'm going to give like 4 to 6. Let's just assume I'm going to do 6. If I don't do 6, then I don't. Oh, let me see. Okay, try those 6 on for size. They get a little interesting at the end. she ducked. It was funny. Believe it or not, for most of these elements, you're not even going to have to look up. You're just going to remember what their charges are, just because you've done it so often. That's the goal. So I'm going to give you guys tons of practice. You'll barely even need a periodic table after a while. So Quentin, what do we have going on today? Yeah.
We have a marketing competition tomorrow.
Oh, okay. You have something next week too?
Yep.
What do you have?
We have like our big prelims and
Like
all that.
competition thing? Okay. The reason I'm asking is my In the Know team has some band members in it in which they're not able to practice. Okay, we about done? Did it get a little trickier towards the end? Okay, here we go. Symbol and charge for potassium. K with A, 1 plus. Sulfide. S with A, 2 negative. Do the charges cancel?
No.
They do not. Lowest common multiple? 2. So therefore, K2S. Everyone 1 for 1? Okay, no. Barium chloride. Symbol and charge for barium. And chloride. Do they cancel?
No.
They do not. Lowest common multiple? 2. Which means we need a single BA and 2 chlorides.
Are you going to mark around and put a 1?
Yes.
Yeah. Okay.
Don't do that.
Does the BA need to be first?
Yes. That's covered right in 1 and 2. iron, 2 oxide. Symbol and charge for iron, everyone. Fe with a 2 plus. Oxide with a 2 minus. Do the charges cancel? They do. So what do we write? FeO, exactly. Is anyone 3 for 3? Not quite half of you. Any questions before I move on? Okay. Chromium 3 oxide. Symbol and charge for chromium. C what? Yeah. And oxide we already know is? Do the charges cancel? No. What's the lowest common multiple? 6. So I need to get 6 positive charges, therefore I need how many chromiums? 2. And I have 2 negative charges, I need to have 6, so I need 3 oxygens. Some of you are possibly crossing over. And if that's true, make sure that you're crossing and not falling. If that makes any sense. Okay. So Cr2O3. 4 for 4. 2, 3, 4, 5, 6. Now's when things get interesting. Okay. Chromium 6 oxide. Well, symbol and charge for chromium 6 is with a 6 plus. Oxide is a O with a 2 minus. So we have kind of a little exception to the rule here. We want to have the fewest particles possible. Now you would say 12, right? In which case you would multiply the chromium by 2 and the oxygen by 6. But that can be reduced. Now many of you have Cr2O6. Is that correct? Did anyone reduce that to CrO3? Did you? 3 of you. Nice. So that's exactly what we would do. It becomes Cr2O6, but we can reduce that to CrO3. We want the fewest particles possible. We're going to find out why later when we talk more about what it means to be ionically bonded. But they're not molecules in the sense that you guys think of molecules. They're more just a bunch of, if you took a bag of magnets and shook them up, would they all order themselves in a pattern such that the oppositely charged sides would be right next to each other? Doesn't matter how big the bag was, right? All right, we're clearly going to leave off here. See you guys tomorrow.
Yeah, see you tomorrow.
Wait, no.